Hello everyone. Today we will learn the basic knowledge about semiconductors. Semiconductor devices are the foundation of modern electronic technology, and they are all made from semiconductor materials. The so-called semiconductor materials refer to materials whose electrical conductivity lies between that of conductors and insulators. Typical semiconductor materials include silicon crystals, germanium crystals, and gallium arsenide compounds, among others. Among them, silicon is the most commonly used semiconductor material. In this chapter, we will mainly use silicon crystals as an example to introduce semiconductor materials and semiconductor devices. As we all know, based on the electrical conductivity, or more precisely, the resistivity of a material, substances can be categorized as conductors, insulators, and semiconductors. Typical semiconductors include silicon, germanium, and gallium arsenide. The simplified atomic structures and crystal structures of silicon and germanium are shown in the figure. As we all know, silicon is a tetravalent element with 4 valence electrons revolving around the atomic nucleus in the outermost shell. For the sake of convenience in analysis, these 4 valence electrons are represented in a planar diagram. When silicon atoms form a crystal, covalent bonds are formed between atoms, as shown in the diagram. Each silicon atom forms covalent bonds with 4 neighboring silicon atoms. A semiconductor with pure chemical composition and no impurities is called an intrinsic semiconductor. It exists in the form of a single crystal in its physical structure. So how does this kind of crystal conduct electricity? This is because the crystal contains thermal energy at room temperature. When the valence electrons in covalent bonds gain enough random thermal energy, they can break free from the bonds and become free electrons, also referred to as valence electrons. As a result, the crystal gains a certain degree of electrical conductivity. It is important to note here that when a valence electron escapes from a covalent bond and becomes a free electron, it leaves behind a vacancy in the bond, which is called an electron hole. This electron hole carries a positive charge equal in magnitude to the electron's negative charge. Compared to the free movement of electrons, electron holes can also move. However, the movement of electron holes is different from that of free electrons, as holes represent a relative movement. For example, under the influence of an electric field E, a valence electron at position x2 breaks free from its covalent bond and falls into the electron hole at position x1. Then, a valence electron at position x3 breaks free and fills the electron hole at x2. This process can be viewed as the electron hole at x1 moving to position x3. This process shows that electron hole movement essentially reflects the movement of valence electrons, and the direction of electron hole movement is opposite to that of the electrons. Therefore, the current generated by electron hole movement represents the current generated by the movement of valence electrons. An electron hole can be regarded as a mobile charged particle, and like free electrons, electron holes also participate in electrical conduction. The free electrons and electron holes that participate in conduction in a semiconductor are collectively referred to as charge carriers. The presence of electron holes is one of the key characteristics that distinguish semiconductors from conductors. Since electrons and electron holes are simultaneously generated by thermal excitation, they always appear in pairs and are called electron-hole pairs. This thermal excitation is also referred to as intrinsic excitation. When temperature changes, the number of thermally excited free electrons in electron holes also changes. This means the electrical conductivity of the semiconductor changes accordingly. In other words, temperature has a significant effect on the conductivity of intrinsic semiconductors. If a free electron recombines with an electron hole during its movement, both the electron and the electron hole disappear. This process is called recombination. Generally, under constant external conditions, the generation and recombination of charge carriers in a semiconductor remain in dynamic equilibrium. Now that we understand the movement of electron holes and free electrons, let's look at a few basic semiconductor concepts. First, what is an intrinsic semiconductor? It is a chemically pure semiconductor. Its physical structure exists in the form of a single crystal. Second, let's define an electron hole. An electron hole is the vacancy in a covalent bond. Third, electron hole pairs are pairs of free electrons and electron holes generated by thermal excitation. As for electron hole movement, it occurs when valence electrons from adjacent covalent bonds successively fill the electron holes. In fact, at room temperature, the charge carrier concentration in an intrinsic semiconductor is very low. Its conductivity still falls far short of the desired level, and it is significantly affected by temperature, making it difficult to meet the needs of normal circuit operation. Therefore, we typically introduce trace amounts of certain elements into intrinsic semiconductors as impurities to significantly alter their electrical conductivity. An intrinsic semiconductor doped with impurities is called an extrinsic semiconductor. The commonly used dopants are trivalent elements like boron or pentavalent elements like phosphorus. When a trivalent element is doped into the crystal, since the atom has only 3 valence electrons, it forms covalent bonds with 4 neighboring silicon atoms but lacks 1 electron, resulting in an extra electron hole. Thus, doping a certain concentration of trivalent impurity atoms generates a certain concentration of electron holes without increasing the number of free electrons. When the electron hole moves away from the covalent bond, the trivalent impurity atom gains an electron and becomes a negative ion. Because it can accept electrons, it is called an acceptor impurity. In this type of extrinsic semiconductor, the majority of charge carriers are electron holes introduced by doping, and these electron holes determine the conductivity of the semiconductor. Since they carry positive charge, we take the first letter, P, from the word positive, to name it a p-type semiconductor. In a p-type semiconductor, there also exist minority charge carriers, free electrons generated by intrinsic excitation. When pentavalent elements are doped, their atoms have 5 valence electrons. After forming covalent bonds with 4 neighboring silicon atoms, 1 electron remains. This extra electron is not bound by a covalent bond and becomes a free electron. Therefore, doping a certain concentration of pentavalent impurity atoms produces a certain concentration of free electrons without increasing the number of electron holes. When the electron leaves the pentavalent impurity atom, the atom becomes a positive ion due to the loss of 1 electron. Because a pentavalent impurity atom donates electrons, it is called a donor impurity. In this type of extrinsic semiconductor, the majority of charge carriers are free electrons. Their concentration mainly depends on the doping level. At the same time, a small number of electron holes are also present due to intrinsic excitation, making them minority carriers. The conductivity of this type of semiconductor is determined primarily by negatively charged free electrons. Hence, it is called an N-type semiconductor, with N taken from the word negative. Doping semiconductors with impurities can increase the charge carrier concentration by tens of thousands to several million times, thus greatly enhancing the charge carrying capacity of the semiconductor. Due to doping, the majority charge carrier concentration in a semiconductor far exceeds that of the minority charge carriers. significantly improving its conductivity and reducing the influence of temperature on conductivity. It's important to note that doping a semiconductor not only generates majority charge carriers but also increases the recombination rate between free electrons and electron holes, thereby reducing the concentration of minority charge carriers. That is, in extrinsic semiconductors, the minority charge carrier concentration resulting from intrinsic excitation is lower than that in intrinsic semiconductors under the same temperature conditions. After understanding doping, let's look at a few key concepts. Impurities have a significant impact on the electrical conductivity of semiconductors, and we can observe some typical data. Doping has a major effect on the conductivity of intrinsic semiconductors. For example, at room temperature, T equals 300 Kelvin, the electron and electron hole concentrations in intrinsic silicon are N equals P equals 1.4 times 10 to the 10 per cubic centimeter. In doped N-type semiconductors, the concentration of free electrons is N equals 5 times 10 to the 16 per cubic centimeter. The atomic concentration of intrinsic silicon is 4.96 times 10 to the 22 per cubic centimeter. These three concentrations differ by approximately 10 to the 6 per cubic centimeter in sequence. It is evident that doping significantly enhances the performance of semiconductors. Just like in our own lives, we need to continuously acquire knowledge and learn from others to keep improving ourselves. That's all for today's lesson. Thank you all for listening.